After this video, you'll look at a rope in a different way. Detailed engineering here. Have you ever wondered how ropes can support so much weight, or how they're able to transmit forces from one point to another so efficiently? Think about the last time you saw a crane lifting a huge load, a climber hanging on a vertical wall, or even a simple fishing net floating in the sea. In all these scenarios, the rope is the silent protagonist. But after all, what makes this seemingly simple element so reliable? And ropes are linear and flexible elements, capable of transmitting forces through tension, unlike bars or beams, which can work in both compression or bending. A rope only works when it's under tension, because if you push it, it bends. This characteristic is exactly what makes it so useful. That's because its flexibility allows it to go around obstacles, pass through pulleys, and wrap around objects, while the internal strands, aligned along its length, share the tension load. But when did we start using ropes? The history of ropes goes hand in hand with the history of human engineering for thousands of years. Long before worked metals existed, plant fibers were already being braided to drag stones, tie up boats, and build shelters. Who here remembers the Tarzan movies? The vines he swings on can be considered the ones that most resemble ropes. Hemp, sisal, and cotton fibers dominated for centuries, thanks to their availability and ease of manufacturing. With the Industrial Revolution, and later with the development of synthetic polymers. In the 20th century, materials like nylon, polyester, and polypropylene emerged, bringing huge gains in tensile strength, durability, and control over properties. At the same time, metallurgy made possible the steel cables that are indispensable in bridges, cable cars, cranes, and elevators. Today, in addition to the classics, there are high-performance materials like aramid fibers or Kevlar, and ultra-high molecular weight polyethylene such as UHMWPE, known as Dyneema or Spectra, which combine high strength with low weight. This evolution not only expanded the applications, but also refined the understanding of how to design ropes for each need. So what types of ropes are we talking about? A simple way to organize them is by material. Natural ones like hemp, sisal, and cotton have good grip and are comfortable to the touch, but they absorb water, lose strength when wet, and degrade faster over time. Synthetics have taken over because they offer more predictable performance, with nylon being very strong and elastic, excellent for absorbing shocks. Polyester has less stretch and great resistance to abrasion and UV rays, and polypropylene is lightweight and floats, which is useful in aquatic environments, although it has less resistance to abrasion and heat. Advanced fibers such as UHMWPE and aramids offer extremely high strength with very low stretch. However, UHMWPE is sensitive to heat from friction, and aramids, although they can withstand high temperatures, have lower resistance to flex fatigue. In addition to these, there are steel cables or wire ropes made of wires twisted or braided into bundles, which are unbeatable in strength and durability. When properly designed and maintained, they are heavier and require specific care in inspection and maintenance. Another way to classify them is by their application in climbing. Dynamic ropes are designed to have a certain amount of stretch and dissipate the energy of a fall, reducing the climber's peak impact. And what about at anchor points for rappelling, technical rescue, working at heights, and speleology, which is the study of caves? Usually static or semi-static ropes with low stretch are used for greater control and efficiency in construction and industry. Ropes and cables are used for tying, hoisting, moving loads, and rigging systems with pulleys in the maritime environment. Polyester and polypropylene are common in mooring lines and anchor cables. But how do ropes do what they do? The principle is physical and elegant, where when you apply a force, the internal filaments go into tension. Part of this deformation is elastic like a spring, which allows it to absorb energy and then return almost to its original length. Another part can be permanent over time due to creep depending on the material and the conditions. The construction of the rope, how the strands are organized and locked against each other, is crucial for distributing the load and controlling the elongation. The internal friction between the filaments and the twisting or braiding pattern prevents the strands from sliding freely, maintaining the shape and distributing stresses. That's why a knot is not just a loop, it creates tight bends that increase friction and prevent slipping. But it also introduces stress concentrations, which can reduce the rope's strength by 20 to 50% depending on the knot. Have you ever thought that a poorly chosen knot can be the difference between safety and failure? When we talk about construction, it's worth looking at the most common construction types. The twisted rope, the classic 3-strand type, is made by twisting bundles in alternating directions. It is flexible and comfortable to handle, but it tends to twist under load and may be more susceptible to surface abrasion. Braided ropes, on the other hand, use interwoven sheaths, which provide dimensional stability and good wear resistance. A very common case is the Kernmantel construction, with a core and sheath, where a core of parallel or slightly twisted fibers provides the main strength inside the rope. While the braided sheath protects against abrasion, UV rays and dirt, modern climbing ropes follow this concept, with the core designed to stretch upon impact and the sheath to protect and facilitate handling. In steel cables, the principle is analogous, where thin wires form strands which ultimately make up the cable, with specific patterns such as 6x19 or 6x36, which balance flexibility and resistance to bending fatigue. But in real use, what matters most? First, the relationship between braking load and safe working load. In many non-critical applications, a smaller safety margin is used. In rescues and work at height, standards and best practices define stricter safety factors and inspection criteria. According to their stretch, dynamic ropes stretch to absorb energy, while static ropes maintain their length for efficiency. Third, the environment, water, temperature, chemicals, and UV radiation affect materials in different ways. Nylon, for example, absorbs water and can lose strength when wet, while polyester maintains its performance better when wet and resists UV rays well. Polypropylene floats, but it is less resistant to high temperatures and abrasion. So you can see that it makes sense to use a floating rope on a lifebuoy, but not on a winch with small hot pulleys. And what about knots then? Knowing which knot you will use is crucial because depending on the type of knot, it changes the behavior of the rope. In pulley systems, for example, the angles and friction change the actual shape at the anchors. And I don't know if you've noticed, curvature also matters because every rope has a recommended minimum bending radius. That's because going over sharp edges or very small pulleys concentrates stress and accelerates fatigue. Protecting the rope with corner guards, sleeves, or rollers is a simple practice that multiplies its lifespan and reduces risks. Visual and tactile inspection is also essential, looking for flattened areas, exposed fibers, bubbles, heat hardening, cuts, discoloration, and contamination with chemicals. In ropes with a core and sheath, localized damage to the sheath can hide problems in the core, and when in doubt, discarding it is safer than taking risks. When well chosen and applied, ropes transform distributed and dynamic forces into something predictable and controllable. And when poorly chosen or mistreated, they can fail abruptly. That's why knowing the basic properties of the material, its construction, and good usage practices makes all the difference. If you've made it this far and enjoyed the video, take a moment to subscribe if you haven't already, leave a like, and activate the notification bell. And if you find our content interesting, consider becoming a member to help us keep producing content here on the platform and be mentioned in our videos. And if you're curious to learn more about the courses we recommend, scan the QR code here on the side or check the link in the video description to have access to various opportunities to develop several skills that will make a difference in your career. And do you use a rope or cable in your daily life? Do you know how to tie a trucker's hitch? Or maybe you already know how to store your rope so it doesn't get tangled. Let us know in the comments down here so we can make the comments section a place to add more information to the video. On the side, there are 2 interesting videos you should watch to expand your knowledge and curiosity. If you'd like to support us, like, subscribe, turn on notifications, and consider becoming a member. Thanks, engineering enthusiasts. See you in the next video.